and kind of definition of what we mean when we say and write radicals. So let's say that I wrote, let me do it more generic than that. I've got an N there. So I read this, what I would actually say out loud is we say the nth root. So I would read that as the nth root, and fancy math word that basically no one uses, what I would put under here is called the radicand. I'm not super big on vocabulary. I have never heard someone use this word in the context of calculus, but that is the name for the thing that goes under the root. We call this symbol a radical. So that's just kind of how we read this thing. I'm hoping that's not new to anyone, but just a couple of things to note about this. Well, this will kind of pop in and out. And one thing that I will just address super quickly is math-wise, we tend to define that. Let me back up. Weird stuff happens when we start talking about negative numbers. Mathematicians had to make some choices about things. So for starters, mathematicians defined that the square root of 25, by the way, I read this special one as a square root. And it's, oops, I missed an E. It's a square root anytime I do not put a number here. The invisible number that we don't write when we mean a square root is that we're putting in a 2. When we write the square root of 25, the answer to this is 5. And our because statement would look like 5 times 5 is equal to 25. Now, the thing that I want to point out is the square root of 25 is defined to be positive 5. Just like the square root of 16 is defined to be positive 16. Now, there's a subtlety here because negative 5 times negative 5 is also 25. So to avoid ambiguity, some now old dudes, mathematicians, had to make a decision, and they defined that the square root of 25 was going to be positive 5. This has consequences when we talk about algebra stuff. So although this statement is also true, the square root of 25 is not negative 5. The square root of 25 is positive 5 always. Okay, good times. So if we don't write something, we mean that it's a square root. If we do write a small number there, then we can have any sort of root that we want. Now, these are some nice numbers, nice kind of common ones to know. When I wrote out all the powers, I gave you a list of things you ought to know. Also, there is a question in the chat, and I'm not ignoring it. I promise I'm going to get there. And so back to my statement about the negative 5 times negative 5 is equal to 25, period. The square root of 25 is positive 5 always. But since the question got asked, I will address it right now. If I asked you to solve x squared is equal to 25, personally, I've got a something squared. I want a 0 on one side of that equal sign so that I can factor that, so that I get that x is equal to 5 or -5. Now I'm going to argue that most of us probably wouldn't go through those steps. When we see x squared equals 25, I think after some practice, most of us would probably go straight to x is equal to plus or minus 5. The reason that x is equal to plus or minus 5 is actually because of this. The square root of 25 is 5 always, never -5. And that's because mathematicians made an arbitrary choice that this was true. So when you're doing algebra stuff, if I'm trying to solve for something and I've got x squared is equal to 25, it is important to remember that I've got two answers to this. The reason I have two answers is really because of this algebra. The shortcut to getting those two answers or to writing those two answers is to go from that x squared equals 25 to say that when you took the square root of both sides, we have to account for sort of the positive and negative versions of it. But that only comes up when I'm solving something. If we're just working with numbers, square root of 25 is equal to +5. I don't know. I hope that helped. It's arbitrary. Like, seriously, you just had to decide. They could have decided that the square root of 25 was equal to both, but they didn't. Mathematicians chose the positive version. And you'll notice if you are actually looking at the textbook talks about the positive square root. So anyway, moving on to some fun numbers. And I promise I'm going to come back to the question about fractions. These are all numbers that, yes, you really ought to know. And when you see them, these are the nice ones. So we've got square roots, cube roots, and usually after a 3, we just go with the number. So next up, I've got 4th roots. So the square root of 0 is 0 because 0 times 0 is 0. The square root of 1 is 1 because 1 times 1 is 1. The square root of 4 is 2 because 2 times 2 is 4. Square root of 9, square root of 16, square root of 25, square root of 36. Basically, we're going to go as high on these. As I said, we should go with their exponent counterparts. I need a little more room. We should also be able to do square root of 49, square root of 64, square root of 81, square root of 100, square root of 121, square root of, anybody know what 12 squared is?
144.
And square root of 13 squared is 169. I would say you ought to be able to get that high in terms of square roots. So if you see 169, you should say, yep, that's the square root of 13. If I go to cube roots, you don't need to know quite so big, but the cube root of 0 is 0. The cube root of 1 is 1. The cube root of 8 is 2. The cube root of 27 is 3. The cube root of 64 is 4. And the cube root of 125 is 5. And I would say that's as high as you should have kind of memorized. If you see a cube root of 125, you should know that that's 5. And for fourth roots, the list is pretty small. We ought to be able to do the fourth root of 0, the fourth root of 1, the fourth root of 16, and I'm going to go the fourth root of 81. And that's probably as high as I would say we need to go. Again, all of these fall in the realm of like nice numbers. I want to pause for a second to just briefly talk about handwriting and reading textbooks. I'm going to take this very last one on here as an example. I'm going to go with, really, at the end of the day, the difference between the two things I wrote is pretty minimal. And depending on your handwriting, it's going to be super important that you have a system to know what you just wrote. When we write the number to indicate the root on the radical, it should be a smaller, so like font size, right? I should be writing this at a smaller size because the subtlety here is I would read this as 4 square root of 81 or 4 times the square root of 81. And the square root of 81 is 9. So that would be a 4 times 9. This over here, it's the fourth root of 81. Meaning, what number raised to the fourth power is equal to 81? This is 3. I don't know why I wrote 31. It's 3. 36 is not equal to 3. So I'm just saying this as a be careful. Be careful when you're writing the problems down. Be careful as you're working through a problem to keep track of your own handwriting. And now I'm going to loop back around to the question in the chat. I think this is why in calculus, we often switch from radical notation to an exponent notation for those radicals, because I think it makes it easier to sort of keep track of what's what. So I'm going to go back to, gosh, was it our first day of class, second day of class, when we were talking additive law of exponents? I am going back to the additive law of exponents for a second to talk about the other notation that we can use instead of radical notation. Quick recap, additive law of exponents. If I had 3 squared times 3 to the 5th, we could write this out, and that's 3 times 3 times, no, it's 2 of them because that's a 2. And we could write this out, and that's 3 times 3 times 3 times 3 times 3. And then we looked and we said, oh, well, that's 7 3s altogether. Or shortcut wise, additive law of exponents, that's 3 to the 2 plus 5, which is 3 to the 7th. Cool. So let's say, just for funsies, I wanted to know what 25 to the 1/2 power was equal to, and I didn't know what it was. Well, using the additive law of exponents, if I multiplied by another 25 to the 1/2 power, then that would be 25 to the 1/2 plus 1/2, which is 25 to the 1. So as an additive law of exponents problem, this says, well, that thing that I didn't know what it was, when I multiply it by itself, I'm going to get back 25. Well, what's the only number that we can put in there? It has to be 5. 5 times 5 is going to give me that 25 we were looking for. For example, if I said the square root of -4, well, if I think about what this radical notation is asking me, the radical notation is saying what times itself was going to give me -4. And there isn't anything that I can put in here, right? -2 times -2 would have given me a +4. 2 times 2 would give me a +4. So the square root of -4, we say is undefined or imaginary. And this imaginary piece, we're not going to talk about a lot in here, but it occasionally, well, it'll definitely show up for those of you that are taking the 17 series for calculus. But this imaginary thing, in case you haven't seen it before, mathematicians got super creative and they were like, oh, -4. We're just going to call that the square root of -1 times 4. And then the square root of 4 is 2. So this would be like 2 times the square root of -1. And some mathematicians imagined that this could be a thing. So they invented this imaginary number that's equal to the square root of -1. In the context of calculus, definitely in the context of algebra or pre-calculus, when we see -4, that means it's undefined. It means that there's no solution. Because there is no real number that when you multiply by itself, you get -4. There is only this lovely imaginary number that kind of fixes it. Unlike square roots, we talk about cube roots. Cube roots of negative numbers are just fine. So this is asking us the question, what can I multiply by itself 3 times and equal -27? Well, if each of these is negative, then a negative times a negative would be positive, times another negative would be negative. So the cube root of -27 is -3. Square roots of negative numbers, undefined. Cube roots of negative numbers just mean that we end up with a negative value. This trend continues in terms of positive roots, negative roots. Also, the commentary back to this, totally agree. Seems kind of unnecessary, but if you're taking 17B, it means really cool math happens. So let me loop back around. So if I said the 4th root of -16, this one, undefined. Because I can't take a number multiplied by itself 4 times and end up with a negative. 5th root, totally fine. Because -2 times -2 times -2 times -2 times -2 gave me a negative number. And 2 times 2 times 2 times 2 times 2 gives me the 32. So to recap, I can take an odd root of a negative number. I cannot take the even root of a negative number. So I'm just going to summarize that as even root of a negative. Nope. odd root of a negative? Yes. The first thing that we would have to note is that there's a restriction because we are only allowed, if we're going to take the square root, to take the square root of a positive number. So our textbook is pretty careful about this to say we're going to simplify that, but let's assume that x is greater than or equal to 0. So that we don't have to worry about, for the time being, that what's inside might be a negative number and therefore undefined. So if I wanted to simplify the square root of x squared, I kind of think about it as the square root and the x squared sort of undo each other, and I'm left with an x. If I wanted to simplify x to the 4th, this is asking us that question, what times itself is equal to x to the 4th? Couple of options to deal with it. Personally, I like to rewrite that x to the 4th to think about it as x squared times x squared, which is going to be my final answer of x squared. Lots of different ways to think about the same thing. If I had the square root of x to the 6th, again, this is asking what times itself is going to give me that x to the 6th. Well, if I had x cubed times x cubed, that would be an x to the 6th inside. Thinking about that additive law of exponents, I'd be taking the 3 plus 3 to get back to the 6. So this is x cubed. You do not have to show me any work on this. You are welcome to go straight from square root of x to the 6th, bam, that's x cubed. If it helps you to write the work out, cool. Well, what if what's inside is less nice? What if this says x to the 7th? This is where those instructions to simplify are really weird, but I'm going to take that x to the 7th and I'm going to rewrite that x to the 7th as x times x cubed squared. I know I'm changing it up, writing things different ways. Hopefully something will click. Well, that means that this x cubed, because he's squared, he can escape the radical. But this x can't escape my radical because he would need an even exponent. This simplified would look like x cubed times the square root of x. I am going to pause for a second. That is, never is a harsh word. I can think of no time in calculus where this is better than this. However, you all have to make it through that placement exam. This is a thing some people care about. Sometimes this is the way, or almost always, this is the way the answer in the back of the book will look. Sometimes a problem will be presented like this. And one of the very first things that I'm going to do is make it look more like that. Because this is going to be easier for us to deal with the calculusiness on. And I apologize because I'm not sure which one of these got blurry and I missed it before. I'll just read them off. This one says x squared times x squared. This one says x cubed times x cubed. And this last one says x times x cubed, whole thing squared. By the way, you might remember doing this with numbers, this kind of weirdness with numbers, like if I needed to take the square root of 32 and somehow simplify that, sometimes what we would do is like break that 32 down and say that that's 2 times 16. And then because 16 is a perfect square, that 16 can escape the radical, but it pops out as a 4. So the square root of 32 is equivalent to writing 4 square root of 2. Again, if we were checking our answer in the back of the book, this is pretty much always how a mathy textbook would write it. It doesn't matter, these are equivalent. Doesn't matter even slightly to me personally, which one of those you write it as. What's important is being able to recognize that they are the same answer, and kind of that ability to go back and forth. So this same idea of simplifying with square roots also leads into cube roots. So for example, if I asked for the cube root of a cubed, this is asking the question, what times itself 3 times is equal to a cubed? Well, that's a times a times a. If I wanted the cube root of a to the 6th, this is asking, is there a way to rewrite a to the 6th so that it is something times itself 3 times, or so that it is something cubed? Remember, powers raised to powers, we're going to multiply those. And if I can write it as something cubed and then take the cube root of it, we get back here to the a squared. We can also mix and match, right? We can have numbers and letters in the mix. So if I were looking at the square root of 81, a to the 4th, b to the 17th. Now that's some garbage, but when we go to simplify this, really similarly to when we were multiplying fractions and stuff, I like to take each piece separately. So first I'm going to think about the numbers, then I'm going to think about one letter at a time. So if I think about the number first, the square root of 81 is 9. So I'm good to go there. That I'm kind of sideways and that came out weird. The square root of a to the 4th is a squared, because a squared times a squared is a to the 4th. But that b to the 17th, little messy. So I'm going to take a minute with that. So that b to the 17th, I'm going to rewrite as b times b to the 16th power. Now the reason that I'm doing that is the b to the 16th, since it's an even number, I know that I can change that to b to the 8th squared. And once I have a perfect square, I'll know how my a turned into a 16. Thank you. Awesome. Much better. Now that I have a something squared, that something squared can come out. I'm like, clearly I need a break. Since I've got a something squared, I can pull that out. But this square root of b, still trapped inside the radical. So I want to like back up a little bit and redo some of the examples we were just doing, but switch gears to think about fraction exponents. Personally, I think this is the easier way to understand it. I think it's the easier way to understand it for variables, and it's definitely mostly the way that we're going to use it in calculus is by using exponent notation. So if I go back to thinking about something like x to the 6th, and then taking the square root of that, if we rewrite this so that that square root we're actually writing as a fraction exponent, the invisible number here when we talk about a square root The thing we don't write is this invisible 2. And as we saw with the additive law of exponents, when we have a square root, that's the same as raising the thing to the 1/2 power. The advantage of writing it like this is I can look at that and say, well, x to the 6 to the 1/2 is the same as, not a 6, is the same as x raised to the 6 times 1/2, or x to the 6/2, or x cubed. You don't have to write any of those intermediate steps. It's just whether that helps you at all. So the other thing is, we're talking fraction note. If I said the cube root of x to the 12th, this means that I've got x to the 12th raised to the 1/3 power. So that same idea with the fraction exponents, when we rewrite it into the exponent notation, whatever the root is, it becomes a fraction when we move that into the exponent. So this is the same as saying x to the 12 times 1/3, or x to the 12 divided by 3, or x to the 4th. I happen personally to think that this is easier to understand when we're talking about variables. I don't know why, but for me, it's harder to think about numbers this way, but we can also think about numbers this way. So if I wanted to deal with the 5th root of 32 and kind of think about it in that same context, well, that's 32 to the 1/5 power. But now I would have to think about rewriting the 32 in some other way. So that 32, I could write as 2 raised to the 5th. And then I can do the multiplication thing and say that's 2 to the 5 times 1/5, or just 2. I don't know why, like, it's just the way my brain works. This is less intuitive for me with numbers. It's more intuitive to switch to fraction exponents for variables. I will also say, I think this is faster to put into a calculator. So if I was trying to put in 32, if I was trying to put in the 5th root of 32 in my calculator, I have a square root button, but I don't have like a 5th root button. So for me, it's faster to type this as 32 raised to the 1/5. That's faster to type into the calculator. So there's a question about, so when we move from the radical notation to the exponential notation, it's true, there sort of wasn't a 1 popping out anywhere in this problem. We have to know that when we go from a cube root to writing it as an exponent, that cube root is going to become the 1/3 power. And this goes back to that additive law of exponents thing. If I had 27 to the 1/3 power times 27 to the 1/3 power times 27 to the 1/3 power, that would be 27 to the 1/3 plus 1/3 plus 1/3, or 27 to the 1. So we kind of just have to know that when we talk about the cube root of 27, it's going to have to turn into a 1/over on that fraction because of the additive law of exponents. I'm looking for these 3 things that multiply together to give me 27 to the 1st power. And the only way to do that with fractions is if they're all a 1/3 power. I don't know if that helped, but bottom line, when we go from cube root to exponent notation, we need to write it as 1/3, even though the 1 isn't sort of anywhere in the problem for us. Good times? Let's have some more fun. So let's say we go back to one of those problems we just did. And suppose that my instructions were to express as an exponent and simplify. Okay, so first of all, if we're going to express as an exponent, there's no number here, which means that we're taking the square root, or the invisible number would be a 2. I could take a minute to write that as 81 a to the 4th b to the 17th all to the 1/2 power. Next, thinking back to how our exponents work, if only multiplication is inside of these parentheses, then that 1/2 belongs to each piece, meaning I can distribute that 1/2 through so that this looks like 81 to the 1/2 power times a to the 4th to the 1/2 power times b to the 17th to the 1/2 power. And then continuing to use our exponent rules, a to the 4th to the 1/2 power is a to the 4 times 1/2, and that's b to the 17 times 1/2. And this I'm just going to go ahead and deal with. Square root of 81 is 9. And simplifying this, I would write that as 9a squared b to the 17 over 2. Personally, that's the choice that I want in terms of doing anything with this in calculus. Different options here. If I'm trying to simplify this, personally for me, I find it easier to treat my number with the radical notation and to treat everything else with fraction notation. That's my personal preference, but that doesn't mean you need to do it that way. That's just how my brain thinks. So when I look at the cube root of 8, I just know that's the number 2. So I would be like, I'm done with that part. It took care of the number thing. Now let's deal with the rest. Well, to deal with the rest, I'm going to say that that cube root is the same as writing a to the 6 b cubed raised to the 1/3 power. And if it's raised to the 1/3 power and all of this is multiplication, then that 1/3 can distribute in to look like a to the 6/3, b to the 3/3. So I'd have 2a squared times b. If you look at that radical and instead it works better in your head to rewrite each of the terms as something cubed, that's totally fine. So if you see that 8 and you think of that as 2 cubed and the a to the 6th, and that's a squared cubed, and the b cubed is, well, b cubed. Then taking the cube root of each piece, we get to the same place, 2a squared b. Totally fine. It's your choice. Just need to recognize that we got different ways to write the same thing. So whatever our root is, when we write it as a fraction exponent, that number is going to go on the bottom. So kind of like super quick. If I write the square root of x, that's the same as x to the 1/2 power, because the invisible number is a 2. If I write the cube root of x, that means x to the 1/3 power. If I wrote the 8th root of x, that's x to the 1/8 power. Or if it's the nth root of x, that's x to the 1/n power. Okay. Let's do another example. I'll leave all of those up. Now sometimes the problem is just going to start with a fraction exponent, and that's totally fine. So we have options here. You can choose to see that and immediately think, oh, I don't really like fraction exponents. I'm going to choose to turn that into the cube root of -27. Totally fine. You might also look at this and say, oh, well, -27 is really -3 cubed. And then that whole thing is to the 1/3 power. 3 times 1/3 is 1. My final answer is -3. You got options. For better or worse, when we're doing math at Davis, we got options. Speaking of options, so I've mentioned that there are some numbers that are sort of the nice numbers that we should be able to look at and recognize, which also means that when it comes to roots and radicals, there are some nice numbers that we should be able to deal with, which then translates to there are some nice fraction exponents we should be able to deal with. For example, if I said something like, we're going to evaluate 32 raised to the 3/5 power. This is a number that we should be able to evaluate without a calculator. And we have choices for how we're going to deal with this. Notice that the exponent this time is not a 1, it's a 3. So when I look at this, we can choose to kind of piece this apart. I can think about this either as saying 32 to the 1/5 power cubed, or I could write this as 32 cubed raised to the 1/5 power. Because either way, when I do powers raised to powers, I'd be multiplying those numbers. So 1/5 times 3 would give me that 3/5 back, and 3 times 1/5 would also give me the 3/5 back. Now, if I have to do this without a calculator, this is the version I want. Because taking the 1/5 power means I'm looking for the 5th root of 32. And that's going to make my number smaller first, because the 5th root of 32 is 2, and I can do 2 cubed. It's not wrong to go down this route. It's just, I don't know what 32 cubed is. And I bet it's going to be really hard to take the fifth root of it if I do 32 cubed. So when I'm talking about numbers and thinking about having to simplify, we can start with either the numerator or the denominator, essentially in that fraction exponent. But when we focus on the denominator first, the numbers get smaller first. Let's do another example. Let's say that I had negative 27. Nope, I'm not going to make that negative. No, I'm not going to make it negative. Let's say that I had, I'm going to make something else negative. 27 raised to the negative 2/3. And I want to evaluate this without a calculator. Well, now in my exponent, I've actually got three things going on. I've got that negative sign, a numerator of 2, and a denominator of 3. So if we're stacking on exponent things together, we have choices for the order, but this is the same as saying 27 to the 1/3 power raised to the negative 2. And if I think about it in this way, my number is going to get smaller first. The cube root of 27 is 3. So now I'm looking at 3 raised to the negative 2. Just a little review of those negative exponents. A couple of choices for how we deal with this. That negative exponent means that really this thing is going to end up in the denominator. If I wanted to write this without a fraction exponent, without a negative exponent, this is the same as 1/3 squared, which is 1/9. You could also here deal with the squared part first and say this is equivalent to 3 squared raised to the negative 1 power. Either route is fine. What is important is being able to somehow walk yourself from 27 raised to the negative 2/3 to evaluating that as 1/9.